two things in parallel. There's the whole series on welding that Professor Eager and Mike Bomford have been going through. I was here yesterday, so I'll do a little tie-in with the aluminum alloy because it's a topic that's also relevant, a lot with design. Today, in terms of my module on use of material, we're going to go into the concept of factors of safety. It's a very general topic. It requires you to understand quite a bit about load analysis and also the strength and capacity of materials. If you're going to evaluate, is this design going to be good enough, there's a lot of factors to take into account, but we'll take a relatively general overview of how people deal with sizing components or selecting materials for a specific application. It varies between industry. That's what you're going to see. So before I get to the factors of safety, I want to go back again to aluminum alloy and also go back to the quality control lecture that I've given last week. Aluminum alloys, if you remember from yesterday, their strength increases when you heat them up, when you age them after the quenching. So if we go through the temperature, time temperature treatment, you expose them to high temperature, so that's temperature and time, and that is to put the elements in solution. At that point, say it's a FCC structure for aluminum, all the copper, all the magnesium, everything is in solution. There's only a single phase, no precipitates. Then very rapidly you quench it. And that's where Professor Eager mentioned about forming residual stresses, because if you have a thick plate and you cool the outside, yes, it will shrink, but the core will prevent the whole thickness. If this is thick, the whole thickness here, the core of it remains hot, and therefore you can have a little bit of stretching of the skin, essentially. It's the same way that you do tempered glass. You cool it down rapidly, and you deform plastically. You exceed the yield strength on the surface on each side, and when everything cools down, you're left with compression, tension, compression. It could be good or it could be bad. It depends on your application. So in the end product here, once you're quenched, you have these residual stressors. Now, you could use the alloy as is in this quench condition, but it's normally very soft because you quench, you didn't have the time to forming the precipitates. What does the precipitates do? They increase your yield strength. They are obstacles to dislocations in aluminum. So what you do, depending on the alloy, I mentioned briefly about rivets, if you remember, rivets for aerospace. What I was saying, it's essentially a 2000 series aluminum alloy. If you remember from yesterday, the tempers, there's a temper, so I'm going to put it here, rivets. There's a 2000 series, have a T3 temper, that's ambient temperature. It means that you don't have to heat it up after here, but you are forming precipitates. And the fact of deforming the rivet to make the joint activate the formation of these precipitates. It accelerates it, and it's also changing how they form. So it's a good combination of design to say, I'm going to quench it, it's going to remain relatively soft, then I do my forming, and over time it gains strength. A lot of alloys, the 6000 series, the 7000 series that Professor Eager mentioned yesterday, what you do is de-aging. So this was the quenching, and here we're going to age the microstructure. It's relatively low temperature, and that's why Professor Eager was saying sometime in service, that aging process could be a cause for deterioration of properties, and that's if you over-age. What would probably help you a little bit here is there's a lot going on after you quench. When you start aging and you start forming the precipitates, there are, depending on the alloy series, but approximately 4 different kinds of precipitates you can form. The first one to form at low temperature are so small, and I'm showing some of them here. You're looking at less than 100 nanometer, little formations of a different composition in the aluminum alloy. So this scale here is 500 nanometers. A lot of them will be coherent, which means that you have a different composition, but your lattice, your crystal is still continuous. It's deformed, but it's continuous. So what happens with something this small is dislocations can still go through it. It will provide some friction. It will increase the properties a little bit, but because the dislocation go through it, it's only going to give you a limited amount of hardening. Then you go through a phase where they are a little bigger. So if we think about this, this is in the aging process. So if we have a particle, and say we have another particle here, and we have the dislocations are always linear defects. So you have a line that's trying to come to these 2 precipitates. If it can cut through it, there's not much going on. If there's enough strain field, enough deformation going around the particles, the dislocation will feel it. It will realize it's coming into a zone where the crystal is not in the minimal energy configuration. It's going to be harder for the dislocation to reach the precipitate. And that's what happens when you start forming loops like this here, where dislocation just goes right in between and it just can't get right over the precipitate. I'm mentioning it because that's where you really gain more in terms of your yield strain, and you also gain a lot of strain hardening. So how much the flow stress is going to increase in plasticity. Well, your stress strain curve here is going to be going way higher, and if you keep going, when we have these curves, if you're looking at this graph here, it's the hardness over time. When you see it's going down, it's because now these precipitates are becoming so big that the dislocation will just come around, and if you don't have a coherent interface, it will just jump around it. Right on that interface, it's a little bit like a grain boundary at that point. It doesn't have to fight and feel. It doesn't feel that there's a precipitate until it reaches it, and then it just goes over. So it's at that point, the precipitate is just too big. So too small, too big, they don't do a whole lot. It's in between, and that's why you go through a peak here. And the exact shape of the precipitate will vary over time. The relevance of it with respect to this class this semester, as Professor Eager mentioned about welding. So in welding, you'll heat up the material in the heat affected zone, and that's essentially what will change this whole treatment. So if you bought, Professor Eager mentioned about 6061 as being a very typical fabrication alloy. It's being welded a lot of time in T6, which is the high strength temper. It's close to the peak hardness. If you have this material, you weld it, so you fuse in some area, and there's another region next to the fusion, the heat affected zone, that gets heated up here and cool down really fast. So you will lose your precipitate in that zone. I'm actually showing this right here. This is to illustrate, Professor Eager mentioned about a factor of 2 reduction in strength. So that is here, this pinkish curve. But for yield strength, it's even more. So depending on what you're designing for, and if you're looking at fatigue, that's the reason why in terms of aluminum alloys, you have to take an additional factor of safety if you're going to weld aluminum. It's not becoming brittle. It's just becoming really, really soft in the heat affected zone. And therefore, if you have cyclic deformation, fatigue, you'll have a chance to form cracks at a lower load. The other aspect that I was bringing up, this data here, is just to show that same thing here in terms of hardness over time. It's going up, then it's going back down. It's an experiment I did back when I was a graduate student where I compared the underage configuration, so smaller precipitate to the larger precipitate here. And what you see in a scratch experiment, so what you're looking at here is there's a conical indenter that's going in this direction out of plane of the sheet. Same loading condition, but you can see that you're forming more pileup, more material is building up on each side of the scratch in this configuration when it was overaged. So again, this is bigger precipitate. The material doesn't consolidate as much because the dislocations start going right through the precipitates as opposed to forming these loops here and essentially multiplying the dislocation. So if you have multiplication of dislocation, everything hardens, you distribute more of the strain, and the material doesn't extrude as much to the surface. Part of this experiment was really to show you can gain more information if you're doing a scratch as opposed to if you do a hardness, because when I went to the lab, ran the hardness test, I get the same number, but when I run this test, I see a bigger difference between them. So it's a test that's very sensitive to hardening of the material, which relates to whether the precipitate are slightly smaller than the maximum hardness or slightly bigger. We will still use overage aluminum alloy, especially in the 7000 series, not because of the mechanical performance, but because they have better corrosion resistance. So that's always comes into the whole decision-making process where, yeah, you want great properties, but also you need to be resisting pitting if you have chlorides in the environment. And that's what bigger precipitate allows you to do better than if you have a very, very fine distribution of precipitates in the alloy. So that's what I wanted to do for aluminum. Any questions? Because we're really sort of moving out of the aluminum. That could be very general. Professor Eager is here too. So they're very useful. They're generally good for corrosion resistance. Although if you fall outside pH of 3 to 9, you lose the natural protective oxide. So if it's in concrete, for example, you can expect more issues. If it's in a very acidic environment, in industrial applications, you just cannot use it. But for atmospheric conditions, if you're looking at building applications or cars, it's normally a great material to use. Pending that you are willing to deal with the reduction in strength during welding. So last time in my third lecture on the use of materials, I talked about quality control, and one aspect that came in was workmanship. When we had the solder joint, I passed it around and essentially said, whether you get a good coverage, a good penetration of the solder in the socket really depends if you're going to do a good sanding job and if you're going to apply the flux and heat it properly. And it's experience, but it's also every single time there's some variation in how you manage to do this soldering process. And it's the same in welding. If you remember, we talked about these roof joists. The roof joists were a tin piece. Here this was a tube, so a tin wall tube for the cord, and we had these bars as diagonal that were a lot thicker. And what I was pointing out, it's not a weld that's easy to do because you have to enter a corner as opposed to being at right angle just doing a fillet weld. We call it a flare bevel That's the name of the detail. And this was an example that didn't work so well because they put all the heat to melt the bar, which is the hardest component to melt, but there's really no significant fusion on the tube over here. And that was an example that was better done. And I mentioned about the tension surface equilibrium here. So when it looks really smooth, it's because you had enough heat, you had the fusion. When it looks really sharp here, it means there was more of a molten metal sitting on, the solid steel tube. So that was more or less the story there, where I said you can have a difference between the quality control during manufacturing, but also a receiving inspection that owners can do, and that we did in that case with the replacement joist. We did talk about rivets, and that was tying with what Professor Eager later mentioned here with aluminum alloy, in getting the material really, really soft because of the quenching of essentially a solid solution, something that doesn't have any precipitate. And then as you go through the deformation process of making the head, you start forming these optimized microstructure that give you a good combination of yield strength and strain hardening. So it's a little bit of a change for today with respect to factors of safety. I'm taking a little bit of more of a general approach. You can design using very prescriptive guidelines, and then if you're doing kind of a prototype, or you're making a new product or a new assembly, you're more or less on your own. You have to decide what your design is looking closest to, so you can have some framework. It's a big framework to be able to specify the material, the quality control, and predicting how it's going to be used when you're talking about load. The example from yesterday about the transmission lines for electricity, I come from a cold country in Quebec, Canada, and one of the issues we had twice was with the towers. So if you have the transmission line and you have these large structure holding them, in the winter, if you have icing conditions and you start building up, so these were the aluminum 1060 between the two columns here. If you start building up ice on the cable and on the towers, there's a lot of framing here, a lot of diagonal. It's some normally galvanized steel, so it doesn't have to be painted, and it's good for an extended period of time. If you build these transmission lines, in Quebec they go all the way from Bay James to Montreal. It's one of the main arteries, and the way they let it out is they don't all come together. They have at least a few 100 kilometers between them. So if there's a big storm in one area, you still get power because it's really all hydro and it's all coming from the north. But in terms of damages and the cost of repair, they decided that it was worth it to arrive to install hardware and software to overheat the lines. So if they used to run the current through 5 wires, and they go for a little bit, half an hour, and run it to 2 wires, these wires are going to overheat, and they use that overheat to melt the snow. It only takes care of what's on the cable. It doesn't take care of what's on the tower itself. But it is an example where clearly back 30, 40 years ago when they made that design, they did not take into account it'll be more ice than a certain amount. And every 30, 40 years we do. And maybe every 25 years. Anyway, they underestimated the amount of ice that was going to form on these conductor insulation. And they found a solution. It was a very elaborate solution, but in terms of overall cost, it was cheaper than going ahead and replacing all the lines. Now, if they had to do it again, they may decide to build a bigger tower. The cost of the raw material is not that much, but the idea of replacing these towers was just very, very, very expensive. So with respect to the factor of safety, what you'll learn from today is how people deal with it very differently depending if it's a car, if it's an automotive, and it already came through this class, but it's one of the things I'm going to emphasize today. If you have a weld, and that ties back to all the AWS discussion we had, this is out of section 2 on design of AWS D1.1 for structural steel. Plates and shapes. What you can see between the base material here, you have an allowable stress range. So we're talking about fatigue here. This is slightly different, where the stress range is essentially your maximum stress minus your minimum stress. It's not the amplitude. The amplitude will be half of this axis. And the life here is what you allow to tolerate. So if we're looking at something that would be under vibration condition, or we don't know how many cycles we get, we'd be looking here at the base material being above 20 KSI, and then the alloy, if it's a joint that's loaded in a transverse direction, so the weld is going, say I have this detail where this is my bar, I have a cut in it, and then I weld this way, and I'm loading in this direction, and then I have an attachment that's in the other direction. It's not a groove weld, it's a fillet weld. You're looking at a stress here that's less than 3 KSI per minute. So it's a factor of more than 5 on what you're permitted. And the main reason is all the residual stresses, the change in microstructure, the heat affected zone, will form cracks in condition where you wouldn't have cracks otherwise. This knockdown factor of 5, as you can see, if I only assume I have a factor of 10 here, 10,000 cycles, is much less. At 10,000 cycles, it will still be allowed to, according to this framework of AWS, to have a stress range of 20 KSI. It's really when you take it to a longer life. So when I mention about making decisions, is if you're looking at a roof structure, how many times you're going to have a lot of snow, and how many times you're going to have wind effects, the uplift from wind and each way, is what allows you to decide how you're going to build the requirements. What sort of safety factor is it? 5, 3, 2, with respect to yield strength. But if it's welded, we're not talking about 20%. We're talking about factors of 2, 3, 4. It's something to keep in mind. So the factor of safety is, by definition, the failure load over the allowable load. But there are other definitions. One of them with the end value here is the yield strength over the working stress. So it really depends how precisely you evaluate your allowable load and your failure load that you're going to have a bigger or smaller factor of safety. If it's a very large structure, the levee in New Orleans, when they had Katrina, had several failures for the reason that it was only built with a 30% margin of safety. And 30% when you don't have the ability to get all the soil data, for example. Soil data in wet condition were very important in that condition. Then do you have plus 30%, or are you missing 30% of capacity on your sheet piling or whatever the structure it is that you're trying to set up, so you don't have any movement? It is unfortunate that we're always cost cautious and cost limited. We wouldn't have as many failures if we were always really doubling what we need to do. What you'll see later, and that's a position that I've came across after working for a while is a lot of things are built so they will last, but not a whole lot more. and so when we see a factor of safety of 3, we can't fool ourselves thinking we can double the load, because it's kind of a fictitious factor of safety, especially with pressure vessels. Pressure vessels, when you apply this criteria here of yield strength over working stress, which is more what they do in the ASME, boiler and pressure vessel code, well, you're not taking into account water hammers, for example. There are a lot of things, and you're not taking into account fatigue. You're just assuming that if you have a material that's 4 times stronger than what will make it yield, you're going to be okay. Which means you can't weld it any way you want if you're going to have a lot of water hammer or pressure fluctuation. Otherwise, you're going to have a failure. So understanding the basis behind these factors of safety is something that, honestly, I've seen a lot of practicing engineers that have been there for a while. They see a factor of safety of 2. They think they're good. They really think that someone can go out and take 30% of it and get away with it. But we don't know. It could very well be that it's only 5, 10, 20% stronger than it needs to be, because it's just about the way it's calculated. So we went to the pressure vessel, the roof joist example here with a factor of safety of 2. It's more of a design based on the overall joist. So they will size so the compression cord doesn't buckle. They will size so the diagonals don't buckle. And then when it comes to the joints, there is a lot of workmanship involved to determine how good the joints are going to be. And whether you have a factor of safety of 2 on the joints, the reality is a lot of times you don't. Whether you get one diagonal that breaks, and either the roof sags or something's happening, and somebody has to go back, show it, and realize, oh no, we don't have exactly what we were looking for. But it's just the way the history has been that people in that industry have been thinking and controlling a lot more the geometrical aspect of the joist as opposed to how the members are actually put together. It's a little unfortunate, but that's the way it is. Now, going a little higher here in terms of quality control, in terms of with aircrafts, in terms of wind load, how much deflection of the wing you get, this is very precise data. When they have a model, they have a working prototype, they go and figure out how much the wing is deflecting during use, and they can go back and evaluate exactly what the stress level is. And therefore, in that industry, when they say, this is my stress, this is my capacity, they use a lower factor of safety, because they know better what they are dealing with in both sides of the equation. So the extreme example of this that I'm aware of is, I put a range as 1.2. I haven't done myself a design of a landing gear, but I'm told that it's about 15% left. 15% between the highest stress that they predict from a load analysis and the lower strength they predict from testing the material. It's very limited. And that's where this load resistant factor design concept comes in. The more you know your load, the more you know your resistance, you can reduce the difference between them. So instead of being 2, 3, 4, 5, or 10, it becomes just 15%. There is a lot, and the reason why there's no consensus that each industry does it a certain way is one of the best way to do a safe design is to base it on something that's already been there, because there's service history in terms of variation. Aircrafts are a good example. Before we had the first crashes of aircraft, we didn't really consider stress corrosion cracking as a problem for aluminum alloys. And by the time we realized it, there's a lot of adjustment that has been made in terms of damage tolerance analysis to account for these cracks, that even though you don't have a lot of loading cycle, it's the time under load. That's what happened in stress corrosion cracking. It's not going up and down, just keeping it up. The environment enables the crack to continue. It's very specific to aluminum alloy and the presence of chloride with exposure to the sea mist. But that industry has to take that into account. If you're working with a steel frame in automotive, it's different. Now you worry about, if the primer is not good, I'm going to have, starting to have some pitting corrosion, and I have to deal with some aspect with the underneath structure. I'm talking about the main frame, not the body itself. But everything is specific. So when you know your use, you know if there's going to be maintenance. In aircraft, they have this checklist of things to do. If you have a car, seriously, the checklist is very, very abbreviated. You have to go for an oil change. They change the filter, but there's not a whole lot done in terms of inspecting the frame. Misuse is something that tends to happen more. For example, I mentioned about snowmobile, ATVs, off-road vehicle. You just go and jump and do all sorts of. So what's the limit? It becomes a little harder. With car, pickup trucks, it's a little bit the same. Obviously, if you go airborne and land on one wheel, it's a lot more load than the average driver. And the question becomes, how many times is someone really going to do that? And whether it's going to create a problem is in terms of demand. What every manufacturer of large volume systems, they have to deal with it. Nobody's going to tell them, well, I want your truck to be able to drop 3 feet, and I want to see the calculation for that. It doesn't happen in automotive. So that's one specificity to them. In terms of capacity, again, the specification, the inspection, especially thinking about welding and soldering, is going to affect really what you're going to get. If you don't have any quality control, I don't know that you can be sure, if you have a joint, that it will have any significant structural strength. If someone can go and do the weld exactly like they want to do it, maybe they didn't put the shielding gas, the things that they really need to do, and if they don't do it, your capacity is not reliable. You may still have it. You're relying on the person's goodwill in that situation, and that's why I decided, in the second lecture, we focused on specification, saying, okay, are you going to weld by AWS, or are you going to weld like you've been told on the previous project? Or what exactly is going on here? That's why it's industry specific. And on the roof joist example, the guy that qualified so well on a repair procedure was a boiler and pressure vessel welder. So for him, this was nothing. It was the easiest joint. You didn't have to do the preheat and the post-weld heat treatment stuff that you can have to do when you're dealing with very high strength steel. So for him, it was easy. And then the next guy who just got certified doing fillet weld and regular groove weld, it was the most complicated joint he's ever made. And just realizing that, if they were able to do the joint we wanted, it was okay for our application, but there will be application where you have to have better evaluation of the welder certification. So I think I made it clear that there are very, very, very few structures that will have a real over-design factor of 4. It's just the way we calculate it. It's just the way we evaluate the demand and the capacity. So why are we doing things the way we do it? There's a lot of history, but there's also lesson learned. In building bridges, they've been doing it with a certain way for so long that to start from scratch tomorrow, because saying, oh, we just put everything into the computer, and computer will allow us to reduce or factor of safety? Well, maybe for the load. Maybe you'll know the load better. But it depends what you put into the computer. Are you going to put in ground settlement on the bridge, which can affect a lot of the stress distribution? If you have one pier, it just doesn't have a foundation that's as stable as the other, it's going down. And that happens on the Longfellow Bridge right here, for example. And well, how do you do with it? Does it affect the overload on some of these main truss structures? The answer is yes. So to the extent that you're willing to not only do a detail analysis is only taking you so much, but if you want to take, oh, what if I have a variation in settlement? What if I have a high wind? What if there's more corrosion here than the average? If you're really willing to go through all that process, is where your calculated factor of safety, you can use a lower value. The more you know, the less of a factor of safety you need. This was a section that I created about another completely different way to look at factor of safety. It's essentially a statistical way. This is the reference. And the idea is, you don't, if we're looking here at the demand and the capacity, there's some variation in both of them. And you take, okay, well, when we're talking about working stress, for example, that would be the point right here. So higher capacity, higher stress, this is the failure boundary. So you put your margin. In this case, looks like we have about 1.5 factor of safety. But then, is it really 1.5? Depends on a lot of variable. Maybe it's a little more, maybe it's a little less. And that's why you create these envelopes. And if you look at it in 3D, in the same axis, resistance and load applied, there's some variation around, if we're taking, for example, a typical value for yield strength. It can be less. It's most likely going to be higher. But the idea with this concept